So I want to go over integration by parts, which you've seen in single variable calculus. And I want to introduce something called the gamma function, which generalizes factorials to real numbers that aren't natural numbers, right? So positive reals that aren't natural numbers. There is a way to define it in terms of complex numbers and whatnot, but we're not going to need that. So we're going to talk about this gamma function. Okay, well, to get there, we're going to need some prerequisites. So to be successful with integration by parts, well, single variable calculus is helpful, of course. You've seen this, it may have been some years for some, which is fine. And then, well, really part of this is integration skills. So really you should know the power rule and maybe rules for integrating e to the x, things like that. That's helpful. And limits will be helpful, of course, as well. And so in terms of integration skills, substitution could be helpful, and your basic rules as mentioned. And the question might be, where can I practice these things? Well, you can practice these for free at a website called OpenStax. Now, this has several free open source textbooks that are approved by the American Mathematical Society, written by some great mathematicians like Gilbert String from MIT. And you'll find books here on not just Calc 1 and Calc 2, but algebra, pre-calc, trigonometry, Calc 3, and beyond. It's a great resource. Okay, so with that said, let's do a little bit of a review of integration by parts. Let's see if we can get everybody on the same page with this. Okay, so what I want you to imagine is you've got some function that's continuous on an interval. Okay, let's call this function u of v. I want to note this is not going to be a rigorous proof because we're not going to consider every case with our function. We're not going to consider if it's, purely increasing, purely decreasing, half increasing, half decreasing, etc. And we're not going to consider it above, below the x-axis and sort of mixed. I'm just going to do sort of a plausibility argument. And what I'm doing now is, in a sense, deriving the formula. Again, this would not be considered to be a full rigorous proof. In order for that to happen, as I mentioned, all cases would have to be considered. Okay, so what I want to do is I want to consider the area here that's under the curve and, of course, above the x-axis. And so, of course, we can say, okay, well, that's the integral from v1 to v2 of, well, our function, we're calling our function u, and the length of a tiny interval would be dv. And what I want to do now is I want to consider a second area. What I want to do is go from the curve to the y-axis here. So from here to here. And then I also want to go, let's see if we can reach there. From there to there. So this will give me a second area that I want to consider. So let's consider this block right here. Okay, so my inputs are v's and my outputs are u's. So let's call this u1, u2. Okay, so here we're going to integrate from u1 to u2. So instead of integrating this way, we're just going to integrate this way, which we know is fine. So that will consider the integral from u1 to u2 of, well, this distance will be v, right? This will be v times, well, a little microscopic length there would be du. So my question now is, what's another way to describe this just using Euclidean geometry, really basic Euclidean geometry? Well, we could talk about this in terms of rectangles, right? Because basically we have this filled in rectangle minus this. Okay, so we just want to say that. So another way to talk about this area, we could say this is, well, pretend it's filled in. So it would be, base times height. So u2 times v2, that would give me this times this. Again, that would pretend it's filled in, but we know better than that, right? It's not filled in completely. It's got all this blank space. So I want to subtract this times this, or u1 times v1. Okay, so both of these are talking about the same area, right? So this talks about this plus this, and this talks about filled in minus this. So of course they must be equal, so we can equate them. So equating 1 and 2 gives us the following. We've got the integral from v1 to v2 of u dv plus the integral from u1 to u2 of v du. That's equal to the expression that we have for number 2, right? So that's nice. But we can sort of think about this. If we're careful, we can actually think about this as an evaluated integral. Let me show you what I mean by that evaluated integral. So yeah, I could really think about this as u times v evaluated from u1 v1 to u2 v2, right? Because you would do this evaluated here minus, by the fundamental theorem of calculus, this evaluated here. And so this is specifically with bounds. This generalizes nicely without bounds, right, to an indefinite integral. The integral of u dv is equal to uv minus the integral of v du. Okay, so there's integration by parts. For those that are familiar, another way to do this, of course, is to start with the product rule for derivatives and then reverse it. Take the antiderivative and solve, you end up here. So I'll do a couple examples of using integration by parts. And usually when people are new to this or they haven't seen it for a while, the part you want to be careful of is just picking out what's u, what's v, what's du, what's v, dv, etc. So feel free to pause here if you need to. Nothing wrong with that. And let's go for an example. Okay, so I'm going to start with a simple example. That's okay. Let's do the antiderivative of x times e to the x dx. And again, thinking about all the bits and pieces, all the parts that we need, right? So I want to decide, so essentially I'm starting with a form like this. I want to decide what's u and what's dv. It's not by virtue of what position they're in, it's by, in some sense, how nice this is to compute. So let's try u is equal to x, and then dv is everything else, including, of course, the dx, right? Okay, so we've got u, there's dv. We said we also need du, which is equal, so that's the derivative, right? The derivative of x is 1, right? So the derivative of x is 1, and that will be in respect to x. So that's 1 dx. Now here, to go from dv to v, you want to take the antiderivative. We know the antiderivative of e to the x is itself. So it looks like we have all the bits and pieces. We'll get confirmation in a moment. I want to be careful. I know there's some mnemonic devices that will work for choosing u and v, but the problem is those mnemonic devices only work for sufficiently chosen problems in Calculus 2. Right? There are plenty of problems for which those mnemonic devices don't work. So I'm going to avoid them. So I just want to, I'd rather go through the reasoning of how to pick this. So this is going to be, so by the formula, uv minus the integral of v du. And we're going to fill this in. So this is u times v minus the integral of v du, and du is equal to dx. I know right now I've got my confirmation that my choice here was fine because this is computable. This is solvable. So that means I only have to take the antiderivative. And so the antiderivative of e to the x is itself. And of course, our constant of integration. Okay, so I'm going to do another example. Feel free to pause here if you need to. Okay, so for example, let's look at the antiderivative of, let's do x to the 6 times the natural log of x. And so here, I'm going to choose u to be the natural log of x. And so dv is going to be everything else, including the dx. So that's x to the 6 dx. Okay, so once I have those, and it turns out if this choice didn't work out, I'd reverse them and try that. And for more complicated problems, you might want to try some trickery, but for us, again, I'm hesitant to talk about mnemonic devices that only work in a few cases because I'm not convinced that's the strongest way to do mathematics. I think we could reason and use logic, and I think that'd be a bit stronger. Of course, if you use those, I'm not judging, just a preference. So the derivative of the natural log of x is 1 over x, and we perform that in respect to x. And then here I need an antiderivative, right? So I'm going to use the power rule. So this is x to the 7th over 7. Of course, I reserve any plus c's to the end of the problem. So this was u times v minus the integral of v du. We're going to fill that in carefully. So we've got u times v. My preference is to write expressions to the left of logarithms and trig, so the reader doesn't think that this is inside of the argument. So I'm going to write u times v like this: x to the 7th over 7 times the natural log of x. And then v du, v du. And of course, we know that the antiderivative here, this is not multiplicative, so I have to, of course, reduce my algebra. So that'll be x to the 6 over 7 dx. And I've got confirmation that my choice here was good because this is certainly computable. If I reverse these, I think I'd run into some difficulty here, and I would say to myself, okay, well, I need to reverse these. And I think that's a worthwhile thing to think through. So this is x to the 7th, so increase the power by 1, divide by that new power. So this will be x to the 7th over 7, but we already have a 7 from before. So 7 from before times another 7 from taking the antiderivative, I get the following. Of course, those that are itching to factor, feel free, but I'm happy with that. Okay, so the point of this was to, I mean, there's plenty of other examples I could have gone through, but the point of this was just to give you a feeler, a little bit of a refresher. If you want to see more, check out the free textbooks at OpenStax. Okay, so now let's introduce the gamma function. Okay, so we're going to say, by definition, gamma of n is defined to be the integral from 0 to infinity of x to the n minus 1 e to the minus x dx. And we're considering n to be strictly positive. And so let's get some practice with this gamma function, right? This is going to be one of the pieces that'll be essential for Friday's talk on half derivatives. So let's say, for example, we want to compute the following. So let's say we want to compute gamma of 1, gamma of 2, and then gamma of 3. And there will be a second, maybe I'll mention that second part now. There'll be another computation that we want to perform. And B, this is a defining property, so show that gamma of n plus 1 is equal to n times gamma of n. Okay, so there's no need to worry, right? We just need to one at a time compute these and just be very, very careful. Okay, so first we'll start with gamma of 1. That means n for n, we're just going to plug 1 in and then compute the integral. So this will input some n and output a value. It'll output a number. So this is the integral from 0 to infinity of x to the 1 minus 1. That's going to be x to the 0, right, when I plug 1 in here. So that will vanish. It'll become 1. That'll be times e to the minus x dx. And remember, in calculus, we tame the infinite in a sense with limits. So this is exactly the limit as b goes to infinity of the integral from 0 to b. That's really what we mean by this. Right? I know some people will plug in infinity, but really, this is how we deal with the infinite here with limits. Okay, so we're going to take the antiderivative of e to the minus x, which of course gives us minus e to the minus x. You can check that. If you take the derivative carefully using the chain rule, you will land back here. So this is indeed the antiderivative of e to the minus x. And we're going to evaluate from x equals 0 to x equals b. Now, if you don't mind, I'm going to rewrite that algebraically before we do this. I always think that's strong, regardless of level. Yeah, for me, math is not a race to the end to get the answer. It's sort of this symphony, hearing all the parts together logically flow. That's why even in personal work, I'll show a lot of steps here. Okay, so I plug in x equals b, and then I'll plug in 0. Okay, so that minus, of course, is from the fundamental theorem of calculus. This minus is from right there. So, of course, that's going to be a plus. And so that's going to give us a positive 1, right? And I'm just going to switch the order if you don't mind. So that'll be 1 minus 1 over e to the b. And now we're going to carefully take the limit, right? So as b gets arbitrarily large, this denominator is going to get very large quickly because that's exponential growth. And this will shrink to 0 in limit. So in limit, we approach the following. So we have our first value for the gamma function, right? So we know that gamma of 1 is equal to 1. All right, so let's go ahead and compute gamma of 2. So gamma of 2. Probably need a little bit more room for gamma of 2. Notice that I did not use integration by parts for gamma of 1 because the x factor vanished, right? So for gamma of 1, there was no need for integration by parts. Okay, so let's see what we have for gamma of 2. That means I'm plugging 2 in for n, and so this will become the integral from 0 to infinity of x, right, x to the 2 minus 1, times e to the minus x dx. And so I've got to take care of this improper integral, right? We take care of improper integrals via limits. And then I notice this is in the form of an integration by parts. Okay, so think about integration by parts. I'm going to let u equal x. I mean, we almost did this problem for the first one. That was just a little different. So dv will be, once I figure out x, dv will be everything else. So e to the minus x dx. And then here I need to take the derivative down. So du is equal to 1 dx. And here I carefully take the antiderivative down. Save any plus c's to the, well, we won't need it. We have bounds. So no need for plus c's. Okay, good. So limit last. And we've got uv. So u times v. Okay, so there's u times v minus the integral of v du. Now, this minus and this minus will make plus. So v du. Okay, so I'm going to integrate that. I can rewrite this, of course, right? So I can rewrite that as minus x over e to the positive x. Now, if I integrate this, I'm going to get a minus e to the minus x. And I can actually write this with a single evaluation bar. I don't want to write this without an evaluation bar. That'd be incorrect. Okay, so of course, I'm going to rewrite that. You could write this with common denominators. You don't have to. It's your choice. It's really your choice. And let's see what we have here. So now I want to evaluate this at b minus evaluate this at 0. Okay, so this is the limit as b goes to infinity. We've got minus b over e to the b minus 1 over e to the b minus, by the fundamental theorem of calculus, now this will be 0 over 1, which is just 0. And this will be 1 over 1 if I plug in 0 here. So that'll be 1. Okay, so think back to Calc 1, single variable calculus. For this particular limit, this is a minus infinity over infinity form. So by L'Hopital's, just for this term, so by L'Hopital's rule, this is the limit as b goes to infinity of the derivative of the numerator over the derivative of the denominator. Again, just for that term, this stays. And now we can just compute the limit. So as b gets arbitrarily large, this term will shrink and get closer and closer to 0. So what do we have here? So this will be 0 minus 0 plus 1 in limit, which is also 1. So gamma of 2 is also equal to 1. So we've got two values of the gamma function. So let's do one more computation. Yeah, let's do that. Okay, so yeah, let's do one more computation with the gamma function. We said we wanted to define gamma of 3. And of course, at any time, feel free to pause, rewind, whatever you need. Whatever you need. Okay, so going back here to the gamma function, we now want to find gamma of 3. Okay, so for gamma of 3, we're plugging 3 in for n. That should leave us with x squared, right? So this is the integral from 0 to infinity. X squared when I plug 3 in for n. E to the minus x dx. Okay, so it'll be a little bit longer, which is fine. So this is the limit as b goes to infinity. I'm going a little faster now if you don't mind, because I think we're all friends here now. And of course, you notice integration by parts. So we're going to let u equal x squared, and then dv is going to equal e to the minus x dx. Du is equal to 2x dx, that's the derivative here. And then the antiderivative, of course, is e to the minus x. Okay, so Let's fill in our integration by parts formula. We're going to notice something. So u times v. So u times v, I'm going to write it like this. Of course, with an evaluation bar, minus the integral of v du. So v du plus 2x e to the minus x dx. And you're noticing we still have a product of functions, right? So we're going to try integration by parts one more time for this. But I'm happy because the power is whittling down, and that seems promising. So for our second round, if you don't mind, I'm going to call this u tilde just to distinguish it from our first round. So that'll be my u tilde, but acting in the same way as u. Right? So dv tilde is e to the minus x dx. Du tilde is 2 dx. And v tilde, this is the antiderivative. Again, this is minus e to the minus x. Okay, so let's fill this in. So this is going to stay there, right? This process will replace this. Okay, so from before we have this. Plus. Okay, so we need u tilde times v tilde, right? So this product right here. And I'm going to write that as minus 2x over e to the x, if you don't mind. That's from 0 to b. So that's u times v, that's this portion right here, minus the integral of v tilde du tilde, so this product right here. So that'll be plus 2e to the minus x dx, and don't forget your balance. So what you're going to see me do now is I'm going to integrate this, and then I'll just write this entire expression with a single evaluation bar. We'll evaluate and then take the limit. We'll have our third value of our gamma function. So pretty rich problem, right? So you're talking about integration. You're doing integration by parts. Sometimes L'Hopital's rule pops up. Okay, so here we've got minus x squared over e to the x. And then here, right, we've got minus 2x over e to the x. And then here, when I integrate, it's going to be 2 over e to the x. See if that makes sense. I'm sure for most it does. But don't be afraid to take a moment to see if that makes sense. And the whole thing from 0 to b. Okay, good. So be very, very careful here. So we're plugging b in. And then minus, so that first term will vanish, the second term will vanish, and then if I plug 0 in here, I'm going to get minus 2 for that third term. Now, typically, I would be careful and show every step of L'Hopital's rule. I think we're going to need one application here and 2 applications here. But for the sake of the video and respect for your expertise, I'm going to skip that if you don't mind. So I'm going to say, after we carefully work this out, and just again to save a little bit of time, we're going to get 2. So let's see what we have so far. So that was gamma of 3, right? So gamma of 3 is equal to 2. We said gamma of 2 is equal to 1, but we also said that gamma of 1 was 1. So we've got a few values. Okay, so yeah, as always, feel free to pause here, work out the details if you need to. Okay, so hold those. And then we're going to look at the next property. So the next thing we want to compute is, let's go back to our gamma function. Okay, so go back to our gamma function. And so for part B, we wanted to look at gamma of n plus 1. Okay, so that just means I'm plugging n plus 1 in for n. So this will be the integral from 0 to infinity of x to the n e to the minus x dx. In fact, a lot of people work with this form of the gamma function. Okay, so yeah, we're going to deal with this via limits. We're going to look at integration by parts, but then we're going to notice something kind of nice. Usually when I teach intro to proofs, when we're talking about a technique of proving that a sequence of statements is true called mathematical induction, I have my students prove something about this, which I'll mention after we go through this. What do we have here? So we've got x to the n e to the minus x dx. And yeah, just following out integration by parts. So we're just going to let u equal x to the n. So u is equal to x to the n. dv is equal to e to the minus x dx. And so du is n x to the n minus 1 by the power rule for derivatives. And v, of course, is minus e to the minus x. Okay, so we've got all our bits and pieces here. Okay, so integration by parts. Let's see here, u times v. Okay, so u times v, I'm going to write it like this if you don't mind. So u times v minus, of course, evaluation bars, don't forget those, minus the integral from 0 to b of v du. So v du. So I'm going to write this in a particular way. So I'm going to have double negatives here for plus. So I'm going to have x to the n minus 1 e to the minus x dx, and that n I'm going to factor in front of the integral, because that's constant in respect to x. So constants can be factored out in front. I'm going to leave it as a little exercise for you to show that this is equal to 0 under this limit. So I'm going to take that for granted again for the sake of the video, if you don't mind. And let's see what we have here. Okay, well, this is constant in respect to b even, so I could factor this out in front of the limit. So that's n times the limit as b goes to infinity of the integral from 0 to b, x to the n minus 1 e to the minus x dx. But this you will recognize, right? What is this from before? That is our friend, the gamma function. Do you see it? That's just gamma of n. So that is exactly this, right? One more thing I'd have to do to make it a little clearer. Remember, I can rewrite this. Maybe you can see it a bit better now. But that's exactly gamma of n there. So that's n times gamma of n. So that's a pretty special property, that this is equal to n times gamma of n. And so with that property, we can make a pretty strong realization about this beautiful gamma function. Okay, feel free to pause here if you need to. Okay, well, since this is actually a statement involving natural numbers, we would need mathematical induction, but I just want to make a little bit of a observation. Not a proof, but an observation here. So I could apply this property over and over and over again, right? So I rewrite this in this following way. So notice that these are just one less than this. So that means that I can rewrite this using this property. So I'd have n times n minus 1 gamma of n minus 1. So do you see how I applied this right here? And then you can, right here, apply this one more time. So that's n times n minus 1 times, how can I rewrite this? Well, it's n minus 2 times gamma of n minus 2. And I can keep going. because I eventually get n times n minus 1 times n minus 2. And then eventually I get down to 2 times 1. But that's exactly n factorial. Okay, so what I usually have my introduction to proof students prove using mathematical induction is that, well, for any natural number n, gamma of n plus 1 equals n factorial. And so what I want to do is I want to look at the graph of gamma of n plus 1. So you can see there is an explicit relationship between factorials and this gamma function. And so here's the curve for a portion of the gamma function, right? And so for n equals 1, notice that I get n factorial, right? For n equals 2, so again, just for n equals 2, I get 2 factorial, which is 2 times 1, of course. For n equals 3, right, you can see that I get 3 factorial, which is 3 times 2 times 1, which is 6. And for n equals 4, for this version, right, for n equals 4, I get 4 factorial, which is 24. And you can see the beautiful thing about this gamma function is that it can answer the question, okay, well, what if I wanted, hypothetically, 5 halves factorial, right? So 5 halves factorial would be whatever y value it corresponds to that point right there. So if I wanted, for example, 7 halves factorial, the gamma function could find it for me because this is generalizing factorials for real positive reals that are not natural. So not just for natural numbers, but for also reals that aren't. And this proves to be quite powerful in statistics, probability, electrical engineering, believe it or not. When we start talking about half derivatives, that applies to electrical engineering. And so this is kind of cool stuff. And so I'll leave you with the following. I'm not going to show you how to do it. If you're familiar with Calc 3 and double integrals and polar coordinates, then it's not too bad, but I'm not going to assume that everybody is. But one of the neat things that we get is that gamma of 1/2, we get this Gaussian, this value called the square root of pi. It's actually a bit of trickery and some multivariable calculus, double integrals, polar coordinates to solve it. Okay, so pretty neat. So gamma function can generalize factorials to non-natural numbers that are real and positive. Good stuff.